Great. All right. Well, first of all, thanks to those of you who got back from lunch in time. I really appreciate that. That's awesome. Yeah. Of course, we've seen lots of examples over the last few days about what authentic inquiry supported by robotic telescopes looks like. I'm really going to bare my soul during this next 10 minutes about the struggles I have with authentic inquiry and what it means and what good it is. And I want to make this a little interactive as well. And because I probably won't get to the end, I want to make sure that the sponsors of the various work I've done are thanked in the beginning. Okay, so a little bit interactive here. Just call out a few characteristics of authentic inquiry. What a feature? What's a
calibration frames?
Real life situations.
Real life, what real scientists do. Research. Student choice.
Data collection.
Data collection.
Data analysis.
Data analysis. Okay. So, communicating results. So here are some of the characteristics in the literature about authentic inquiry. And of course, I mean, John Dewey back in the 40s, 50s, and 60s was talking about authentic inquiry. It's not recent. But these are some of the characteristics: real world, meaningful problems, having the characteristics of professional scientific inquiry. I think that's what you had in mind. Driven by learner's own questions, student choice. The learner may control more of what happens, designing the, there's this community of practice aspect I've heard. And then one of the questions I'm dealing with a lot is, what do we mean when we say authentic inquiry? People mean a lot of different things when they're talking about that. What does it have to be resulting in a research paper? Is it authentic if it's authentic to the learner, or does it have to be authentic to the scientist? So I have all these questions and I struggle with them all the time, and you might too. But what's it good for? So now a few things call out what it's good for. Why do it? Motivation.
Ownership.
Ownership.
It allows students to experience what it's like to do research.
Experience what it's, the experience of what it's like to be a scientist. Critical thinking.
Self-efficacy.
What
Reflects what the world is
reflects what the world is like. Building self-efficacy. So we have some differences here between kind of outcomes and experiences. And so here are the claims about authentic inquiry, right? And generally they fall in these four categories. Helps students learn content. It helps them experience scientific practices. It helps build interest and motivation. And maybe this term we're now really trying to build called STEM identity, or the idea that I see myself as a science person, and possibly the fact that it integrates all these things at once, right? It integrates all these things at once. So that's the claim. What should we be looking out for? And of course, the skeptics say, students, authentic research is really a lot for some students to handle. There's a lot of things you're juggling. It's very difficult for teachers to manage in a classroom authentic inquiry. We've talked about all the demands teachers have, and so it's a very hard thing to integrate into the classroom, or it can be. Some people say, well, when you do authentic research, it takes a long time to actually learn the concepts because the data is so messy, and of course, we might consider that a plus. I have this research report up here because it's in our group. We did this survey of college freshmen, 8,000 of them nationwide, looking at their, one of the things we looked at was their experience of self-directed projects, And unfortunately, at least this particular research study showed a negative correlation between the amount of self-directed research projects and their performance in freshman science classes. So, so there's caveats all around. Okay.
Is that test-based assessment evaluation? Did they measure success via a test?
I can talk to you afterwards. I want to get my 12 minutes in. So I'm gonna focus on two projects. Although, as you heard from Frank the other day, we have 20 years of projects with Micro Observatory, where we're really asking, okay, how does authentic inquiry have value beyond what is more traditional in classrooms? And that's one of the reasons we're all in it. So the two projects are our exoplanet project, in which students use our 6-inch micro observatory robotic telescopes to gather data on hot Jupiters, and our Youth Astranet project, which is an NSF-funded community of learning. So I'll go through both of these pretty quickly. I want to talk about, so the ExoLab project is highly scaffolded. Okay, it's highly scaffolded, and we incorporated design features that respond to the research, and I'm particularly citing Edelson, Golden, and Roy P., who's a great person to talk about supporting inquiry through technology. And these are some of the design principles. You want the problem, and we all think all our astronomy problems are meaningful. They have implication in exoplanets. Are there other worlds? Implications that matter. We incorporate staging activities, bridging activities to bridge the novice to expert gap, embedded information sources, so the kids don't have to go all over everywhere to find out information. There's things linked right as they're doing the work. And record-keeping tools, all in a browser-based platform. And you can get to this browser-based platform. We currently have 450 educators around the country who used it. That's about 18,000 students who have user accounts in our ExoLab. Most of them are high school, although we are getting increasing numbers of community college and Astro 101 kinds of courses. So the lab walks you through this series of modules. You can see at the top a modeling lab where students predict, and this is you draw this, they predict what the graph, so they're manipulating multiple representations, the visual model with the graphical model. They then make requests for images over the night, and the teacher can separate that out so that each student's getting 10 of the 100 images that are available that night. They then go on the next day, those images come back, and there's a built-in photometry tool, but it's kind of a manual photometry tool to unpack what's going on. What are you really doing when you measure the brightness of a star? And so students actually are using their cursor to, I know I have a pointer here, don't I? I don't have to go over. Oops, but I pushed it forward when I did that. So students measure the target star, 2 comparison stars, 2 pieces of background sky, and it kind of unpacks what you're doing, and the idea that you're using controls. So once you do one image, you get 1 point. There's a built-in graphing tool. When you roll over any point, you can see which student did that point. So as the class is looking at the data, as they're all doing it, they say, wait a minute, who did that point? What's going on at those? Is it the data? Is it a person? How do we know? We have some tools for analyzing that. You can look at the raw components, so you can see things like signal to noise. All of science is really about finding a signal and the noise. And so that's the 2 comparison stars in red, the target star in green. Somebody obviously measured the wrong star here. And here, there was something strange between 11 and 12 that happened. That might be that one that's up there. Anyway, so. Here's an example of when signal to noise is going down, and it's a very messy night. And so you get really messy data sometimes too. There's a modeling tool where you can explore the parameter space and do a best fit just with your mouse and cursor, and then compute the size of the planet from the depth of the dip. And there are other tools. I'm really breezing through this really quickly. I apologize for that, but I just wanted to give you a sense. So now the results. Okay, what value was this authentic inquiry? Can students mobilize their existing knowledge? We said one of the claims is that authentic inquiry helps people apply, helps students apply. And so these results, which so in the modeling lab, you know, we have the embedded answers of this is from a field test of about 1,500 students. And these are 2 classrooms. So I'm just picking 2 classrooms. In the embedded answer where they describe what happens, why the graph has a, you know, why they predict a dip like that. Qualitatively, most classes, here's 2 classes, pretty much every student can describe that. But when asked to make a quantitative prediction, if the planet is 1/5 the diameter of the star, what % dip will there be? Then you get a large variety between classes. So here are those same 2 classes quantitatively, and this is before and after, I should say. Before and after, we asked that question twice after they've done it. So, but it's hard for students to understand. So that quantitative aspect of understanding a transit model. Whoops. Some more qualitative response. One thing students definitely learn is how to assess the factors that affect their data. So here's a before and after text cloud thing of when students are asked why does your light curve look different than the nice one you predicted. Here it's all because I did things wrong before, and then later, after they've gone through some of that analysis of their components, you see actual factors coming up: the haze, the horizon, the altitude, issues like that. Okay, so the good news: content learning gains. We did get content learning gains in doing this. The caveat. Hierarchical linear modeling showed that this was very dependent on the teacher. A lot of the very dependent on the teacher. The somewhat bad news and interest goes down. Okay, in this forced mark that teachers do in the lab. This is a field test. These are the teachers' first time. The students are less interested, although they are, these 2 significant gains, 0.74 and 0.36, are students' self-rating of how much they know. So again, they learn some about exoplanets and they think they learned something about exoplanets. The second project, which I know I only have 2 seconds for, so I'm gonna, 1 minute? Okay, can I show a 3-minute video and then be done? I'll show a 3-minute video and then be done, and we can ask questions. So another one where we purported to show authentic inquiry, and it's quite a different kind of authentic inquiry than the ExoLab project.
Program to teach astronomy. With Youth Astranet, a program to teach astronomy through digital astrophotography, we strive to capture the scientific wonder all children feel, with a particular focus on cultivating the science identities of girls and minority youths. Youth Astranet succeeds because success depends on the people involved. We have the facilitators and educators who run the program. We have the team at the Smithsonian Astrophysical Observatory who provide continuous support. And of course, we have the students. There's there's still a few considerations to address if we want to help build science identities. First, how do we prepare and support educators? Most of our participating educators don't know much about astronomy or astrophotography to begin the program. To get ready, educators join us for live training webinars, office hours, and one-on-one tutoring. We take them through the ins and outs of our image capture and digital processing tool. Second, how do we get sustained engagement from the kids? Well, the experience is creative, it's meaningful, and it's real. The technology is real, the photos are real, and the editing and analysis are real. Students across the country access their unique workspaces in the Youth Astranet portal. Here they place requests to our telescopes to take pictures of various objects in the sky.
And then we process them, so we colorize them and we put in different filters to see the desired effects.
The students then must analyze the embedded information, the same way real scientists at Harvard and Smithsonian do every day, many of whom offer to serve as mentors and answer questions from the students.
Is it possible for humans to live on other planets? Have you worked on any robotic creations? How are stars ripped apart by black holes?
Among all this real science and technology, students can get really creative.
I took 3 images of the Orion Nebula and I added a filter to each of those images. So I added a red filter to one image, a green and a blue to the others. And I was able to align them perfectly so it looks like the real thing.
Eventually, the students and educators together decide how to present their portfolio of work in a capstone project. Every student creates something substantial that lasts long after the program has ended. This is a piece of work that demonstrates their new mastery of astrophotography, and it gives them an opportunity to imagine their own place in the world of science. The final consideration: how do we know if the program is achieving our stated goals? Well, first, we conduct pre- and post surveys with the students of every program. Second, we observe how students are interacting with the Youth Astranet portal. In many cases, students use the website outside of program hours in their free time. Third, we talk to the participants themselves.
I think being an engineer would be cool now. Like I said, I did not like space, and now I think it's really interesting and cool.
But there's still more to discover out there, and I'm curious to learn more.
I would like to give a shout out to my mom for letting me do this program. I really enjoyed it.
You just go right to the last slide. So anyway, so I had lots of slides on the actual results of this very different looking authentic inquiry with telescopes. And the last slide, I'll go. Oh, wait. There's the last slide. So these are my parting thoughts. And if there's any questions, I'll take, I guess I have room for one maybe.
Yes. Thank you. Let's all thank Mary. Any questions?
Yeah. How much can you handle expanding the program? So the Youth Astranet currently is NSF supported, and so every student we have to get informed parental consent. It's an IRB project, so we're only allowing in those who are participating in the research and who agreed to do that. Ultimately, microobservatory is there are some scale issues, and that was one of the slides I skipped, but the microobservatory can accommodate thousands of students per night. It's the support of the educators that's the scale issue here. And I think that's for all of us. That's one of the things for all of us to think. The scale, there's 54 million pre-college students in the U.S. Can we get the 4 million 8th graders in the U.S. all to have an experience with robotic telescopes? That's what I want to know. Yeah.
I see a lot of applications for the really awesomely cool tools you built. Do you have documentation on the programming and the code? Do you share that? It's an NSF project.
Yeah, we're still in the middle of the NSF project. Yeah. So the programming.
Are you documenting the programming development in such a way that you'll be able to disseminate and share how you built all your stuff?
when you say programming, do you mean educational programming
The
or
coding,
code?
the coding.
Okay.
Yeah, coding, if we want to steal your cool tools.
Yes.
Yeah.
Yeah.
Steal your cool tools.
Yeah, it's all open source.
Yeah.
The JS9 image processing is open source. Yeah.
Okay, let's thank Mary once again.